Today, when I normally talk to you about a research paper, it's typically about AI, but I want to talk to you about a physics research paper today. It's called Fundamental Limits for Realizing Quantum Processes in Space-Time. I bring up this particular research paper because it aligns very closely with how I model physics when I'm building out my AI models. When I build out my AI models, I do make certain assumptions regarding physics and specifically with regards towards dimensionality. My assumptions are that the models use topology and shape to learn via the data process. That it's kind of like quantum topology, that they utilize quantum shape. Essentially, they shape and reshape the data in order to learn from it, and they utilize dimensionality in order to do this. So they'll shrink it down to one dimension, explode it up to hyperdimensional space, meaning like 10 dimensions, multiple dimensions, etc. It's very hard for the human brain overall to think about more than three dimensions overall. And that's what this research paper hints on and is all about. So this research paper, Fundamental Limits for Realizing Quantum Processes in Space-Time, very specifically makes an argument that quantum mechanics and quantum physics is kind of a dimensional overlay on top of relativistic physics, that both exist at the same time, and it kind of serves to unify the two. It's just that they both exist within the same space, but different dimensions, and that's a hard concept overall for humans to process and to think about, right? And then so again, going back to that concept of dimensionality, we live in a universe, in a world of three dimensions. We're very used to three dimensions and how that operates. Thinking beyond that tends to have us run into limitations with our thought processes. If we think of the universe more of like a hypervector, it would be like 1,000 dimensions. And then the three dimensions are just the dimensions that are visible to us. And then there would be other dimensions that exist that impact and influence our calculations that aren't within our observable reality. And then taking this concept, we can look at other concepts such as light, color, the color spectrum, etc., that we know intuitively as children, all since childhood, all fall within the spectrum, right? We're taught since childhood that there are colors that we can't see. And then, for example, like our universe as a whole is kind of dictated by that color concept, right? Me as a male, I see just intuitively half the amount of colors as a female. Like I have less cones in my eyes when it comes to colors overall, and the ability to see, and that shapes my reality. I have less dimensionality when it comes to colors. And intuitively, we understand that it's the same way with light, right? That there's light that exists on spectrums that we can't see on a human scale. And then so it would be the same thing with dimensionality. And so what this research paper proposes is that, and mathematically, very elegantly mathematically lays out through multiple theorems that essentially quantum physics in this aspect, these dimensions of quantum physics can operate and interlay directly with relativistic physics overall. And then specifically, this goes into and talks about and dives into the quantum superposition with regards towards causality. And then so within relativistic physics, I actually made a video on this quite recently, right, where you never can think of a concept of an egg being uncracked. The egg is always cracked, right, because kind of causality only moves in one dimension, and only one way, only forward. But that's a consequence of relativistic physics and not quantum physics. And then so in quantum physics and quantum land, you could have instances or probabilities that exist where an egg is able to uncrack itself. And then so what happens is that reality exists as an overlay on top of the relativistic dimensions that exist. So in our relativistic universe, the egg can never uncrack itself, even though it could if we were operating in purely quantum dimensions, right? It's this overlay, like the glasses don't, the overlay doesn't actually impact the further structure, the inner structure, which is the relativistic physics in this aspect, right? And so that's kind of the key point within this, is that this doesn't, like, the two are very compatible under this theory, that essentially anytime that you would have an issue where you have kind of incompatibility, generally speaking, under this theory, what they kind of lay out is that relativistic physics would trump or supersede the quantum physics within this particular aspect. And so, just lastly, the last thing that I'll note within this, the thing that they mention very specifically within this paper, and as a result of this, is that all of the math checks out within this research and within their research, but they acknowledge and they understand that within this research, it means that we have to essentially change our understanding of space-time very specifically with regards towards how it functions within our current understanding of physics overall, which again very much aligns with why this research paper caught my eye in the first place. Very specifically, the simple calculations that and adjustments that I make within my models to space-time is that I treat space-time as a multidimensional variable in and of itself within my calculations, and whether that be the Einstein equation, the Schrodinger equation, Hamming distance, whatever I'm calculating, I change the equation so that very specifically space-time itself is a singular variable and is a multidimensional variable that I can play with, and it works with all of my mathematical calculations, and it works with everything that I do. Aligns with this research here, and more research is aligning and culminating on these things. And then so just pointing out, highlighting this out, I thought this was a cool paper overall, because when it comes to AI models, how they learn very specifically, again, I'm very big on topological learning. I think that's very specifically how they're learning and what they're doing with the data. And all of this aligns within this, right? Within that, right? It's essentially topological learning via quantum geometry. And so if you like this type of content, please like and subscribe. Thank you very much.